Hello friends, hope that you have gone through notes pertaining to heat exchanger shared during the last week. In this session, we will discuss numericals related to heat exchangers. The objectives of this particular session are to have a review on LMTD method, to do numericals on LMTD method for parallel flow and counterflow heat exchangers. First of all, let us have a quick review on parallel and counterflow heat exchangers and their temperature distribution. This is a parallel flow heat exchanger. In a parallel flow heat exchanger, hot and cold fluid moves in the same direction through the heat exchanger. We can see that the hot fluid and cold fluid are moving in the same direction along the heat exchanger. Due course of its motion, heat will be transferred from hot fluid to cold fluid. Let us see the temperature variation of this fluid along the length of the heat exchanger. For that, let us plot the temperature variation of the fluid on y-axis and length of the heat exchanger on the x-axis. Here we can see that the hot fluid temperature decreases in this particular direction along the length of the heat exchanger as it is losing heat. Consequently, the temperature of cold fluid increases when we move from inlet to exit of the heat exchanger. This is because it is getting heat from the hot fluid. If you consider, on the other hand, for counterflow heat exchanger, we can see that in a counterflow heat exchanger, hot fluid and cold fluid are moving in opposite directions. If you consider the temperature variation along the length of the heat exchanger, the hot fluid temperature decreases in this direction. This is the direction of motion of hot fluid. So hot fluid temperature is moving in hot fluid temperature is decreasing along the length of the heat exchanger. Whereas you can see that cold fluid is moving in this direction, and you can see that the cold fluid temperature is increasing in this particular direction. So there's a difference in temperature profile for for a parallel flow and a counterflow heat exchanger. Before going into analysis, let us see the nomenclature and notations used for the analysis throughout. Suffix, if C is used as suffix, that means it is cold fluid, and on the other hand, if H is a suffix, it is hot fluid. Suffix 1 represents inlet condition of the fluid, and suffix 2 represents outlet condition of the fluid. In addition to this suffix, we have some other notations also. Cp, you may probably know that Cp is specific capacity of the fluid in kilojoules per kilogram degree Celsius. M dot represents mass flow rate of the fluid in kilograms per second. Delta T or theta represents temperature difference, and T represents the temperature in degree Celsius. Now let us consider a heat exchanger. Consider parallel flow heat exchanger. You can see that hot fluid and cold fluid are moving in the same direction. Hot fluid is moving through one channel, cold fluid is moving through another channel. These two channels are separated by a solid wall which is having high thermal conductivity, through which heat is transferred from hot fluid to cold fluid. Let us see the inlet temperature for hot fluid, how it is represented. TH1. What is H? H is suffix H means hot fluid. One represents inlet condition. So TH1 means temperature of hot fluid at inlet. When it moves out, it is temperature of hot fluid at exit. 2 means exit. Similarly, TC1 is temperature of cold fluid at inlet, and TC2 is temperature of cold fluid at exit. When the hot and cold fluid flows through the heat exchanger, heat will be transferred from hot fluid through this separating wall to the cold fluid. Basically, this is a multi-mode heat transfer. Heat from the hot fluid is convected to the separating wall. That heat convected is conducted through the wall that separates hot and cold fluid, then it is convected to the cold, then it is convected to the cold fluid. So it's a multi-mode heat transfer. Now you can account the heat lost by the hot fluid and heat gained by the cold fluid. Heat lost by the hot fluid can be accounted by considering the mCp delta T experienced by the hot fluid. That is, Q is equal to m into Cp into delta T experienced by the hot fluid. Hot fluid, the temperature is decreasing from inlet to exit, so higher temperature minus lower temperature. Similarly, the heat gained by the cold fluid can be accounted as Q is equal to mCp delta T, mass of the hot fluid, Cp of the mass of the cold fluid, Cp of the cold fluid, and delta T experienced by the cold fluid. Since the temperature of the cold fluid is increasing, Tc2 minus Tc1 is represented. Why? Because higher temperature minus lower temperature, Tc2 will be higher. Tc2 is temperature of cold fluid at exit minus temperature of cold fluid at inlet. Next is heat exchanger analysis. Heat exchanger analysis is essential for the design and fabrication of heat exchangers. This can be done through two methods. First one is LMTD method, or logarithmic mean temperature difference method, and second one is effectiveness NTU method. We will start with LMTD method. Before going to the method, let us see what is LMTD, or logarithmic mean temperature difference, and why it is required. Consider a heat exchanger. We have considered a parallel flow heat exchanger. See the temperature variation of hot and cold fluids along the length of the heat exchanger. You can see that the hot fluid temperature is decreasing along the length of the heat exchanger, whereas cold fluid temperature is increasing. In addition to this, we can see that the temperature difference between the hot and cold fluid is not a constant in actual practice, and it is varying along the length of the heat exchanger. If you consider the inlet section, the difference is larger compared to that of the exit section. And this temperature difference is varying throughout the length of the heat exchanger. So it is difficult to determine the total heat transfer from the hot to cold fluid under this condition of varying temperature difference. So for the sake of simplicity, we assume a constant temperature difference that would give same heat transfer that actually occurs under variable conditions of temperature difference. That is, in actual practice, even though the temperature difference is varying, we replace this varying temperature difference with a constant temperature difference that gives the same heat transfer rate. This constant temperature difference is known as LMTD, or logarithmic mean temperature difference. Now let us see the definition of LMTD. LMTD, it is defined as that temperature difference which, if constant, would give the same rate of heat transfer as actually occurs under variable conditions of temperature difference. Actually, the temperature difference is varying throughout the length of the heat exchanger. So we can see that at this section the heat transfer is due to this temperature difference, whereas this section it is due to this temperature difference, this section it is due to this temperature difference. Right? So this varying temperature difference we are going to replace by using a constant temperature difference that gives the same heat transfer rate that occur under variable conditions of temperature difference. This is what we call as LMTD. So if you assume such a constant temperature difference, you can write the total heat transfer rate in the heat exchanger by using the equation Q is equal to U into A into theta M. It is same as U into A into delta T, where U is the overall heat transfer coefficient, A is the area available for heat transfer or the heat exchanger area, and theta M is the temperature difference. That's the constant temperature difference, or theta M is the logarithmic mean temperature difference. Now, the logarithmic temperature difference method, or LMTD method, is used when the inlet and outlet conditions of the fluids are known. or LMTD method can be easily applied when inlet and outlet conditions of the hot and cold fluids are known. Normally, LMTD method is used to determine heat transfer rate associated with the heat exchanger or heat transfer area associated with a heat exchanger. LMTD method is based on certain assumptions. They are: the overall heat transfer coefficient U is constant. That is, the value of overall heat transfer coefficient U is same throughout the entire length of the heat exchanger. Next, flow conditions are steady. That means the mass flow rate of hot and cold fluid are constant. Next, the specific heats of both fluids are constant. That means specific heat of hot and cold fluids are constant. Next, there is no loss of heat to the surroundings due to the heat exchanger being perfectly insulated. That means in heat exchanger, there is only heat transfer from hot fluid to cold fluid, and there is no heat transfer from the fluid to the surroundings. So for that, we will consider the heat exchanger is completely insulated from the surroundings. Next, there is no change of phase either of fluid during heat transfer. That means the hot fluid and cold fluid, it won't undergo phase change during the heat transfer. The cases with the phase change will be dealt separately later. Next, the changes in potential and kinetic energies are negligible. Next, axial conduction along the tubes of the heat exchanger is negligible. That means there is no heat conduction along the axial direction or lengthwise direction of the heat exchanger. There is heat exchange or heat transfer along the transverse direction, that is from hot fluid to cold fluid. Derivation of LMTD for parallel and counterflow heat exchangers has been shared during the last week. Let us have a quick review on the methodology used for the derivation of LMTD for parallel and counterflow heat exchangers. Consider a parallel flow heat exchanger. As I mentioned earlier, the temperature difference between the hot and cold fluid varies continuously throughout the entire length of the heat exchanger. To find out the total heat transfer rate associated with the heat exchanger, we will consider an elemental section of the heat exchanger, and we will evaluate the heat transfer through the elemental section, and the heat transfer through the elemental section, if it is integrated over the entire length of the heat exchanger, we will get the total heat transfer rate associated with the heat exchanger. So let us consider an elemental section of the heat exchanger with heat transfer area dA. Let TH and TC be the temperature of hot and cold fluid in that element respectively. Then the heat transfer rate through the elemental section is given by dQ is equal to U into dA into delta T, where dA is the heat transfer area associated with the elemental section, and delta T is temperature of hot fluid minus temperature of cold fluid. If this expression is integrated over the entire length of the heat exchanger, that gives the total heat transfer rate associated with the heat exchanger. So if we integrate this heat transfer rate for the elemental section over the entire length, we will get equation number 1. That is, total heat transfer rate Q is equal to U into A into theta 2 minus theta 1 divided by ln theta 2 by theta 1, where theta 1 is the temperature difference between the hot and cold fluid at the inlet of the heat exchanger. That is theta 1 equal to TH1 minus TC1, and theta 2 is the temperature difference between the hot and cold fluid at the exit of the heat exchanger. That is theta 2 is equal to TH2 minus TC2. We have the expression for total heat transfer rate Q in terms of LMTD as Q is equal to U into A into theta M. Take it as equation number 2. Comparing 1 and 2, or equating 1 and 2, we will get the expression for logarithmic mean temperature difference, that is LMTD is equal to theta 2 minus theta 1 divided by ln theta 2 by theta 1, which is equal to theta 1 minus theta 2 divided by ln theta 1 by theta 2. Similarly, if we consider the case of a counterflow heat exchanger, we have this temperature profile. Consider an elemental section of the heat exchanger where the fluid temperature is TH for hot fluid and TC for cold fluid. Then you can write the heat transfer through the elemental section of the heat exchanger dq is equal to u into dA into Th minus Tc. If you integrate this heat transfer expression over the entire length of the heat exchanger from inlet to exit of the heat exchanger, we can get the expression for total heat transfer rate through the heat exchanger, which is represented by equation number 4. Q is equal to U into A into theta 2 minus theta 1 divided by ln theta 2 by theta 1. Again, if we compare this total heat transfer rate with the total heat transfer rate in terms of LMTD, that is equation number 2, equating 4 and 2, we can get LMTD for a counterflow heat exchanger as theta m is equal to theta 2 minus theta 1 divided by ln theta 2 by theta 1, which is equal to theta 1 minus theta 2 divided by ln theta 1 by theta 2, where theta 1 is the temperature difference between the hot and cold fluid at the inlet of the heat exchanger. Here theta 1 is Th1 minus Tc2, and theta 2 is the temperature difference between the hot and cold fluid at the exit of the heat exchanger, and theta 2 in the case of a counterflow heat exchanger is Th2 minus Tc1. Now let's compare the LMTD of parallel and counterflow heat exchangers. This is the expression for LMTD for parallel flow heat exchanger, and this is the LMTD expression for counterflow heat exchanger. Even though these expressions for LMTD seems to be same, the values of LMTD for parallel flow and counterflow heat exchangers are different. This is because theta 1 and theta 2 values for parallel flow is different from that for a counterflow heat exchanger. For parallel flow heat exchanger, theta 1 is Th1 minus Tc1, theta 2 is equal to Th2 minus Tc2. Whereas for counterflow, theta 1 equal to Th1 minus Tc2 and theta 2 equal to Th2 minus Tc1. So under similar conditions, if we calculate the LMTD for parallel and counterflow heat exchangers, always the LMTD of a counterflow heat exchanger will be greater than that of a parallel flow heat exchanger. Under similar condition means, consider this heat exchanger, it's a parallel flow heat exchanger. You can convert this heat exchanger into a counterflow heat exchanger by reversing the direction of cold fluid. So it becomes a counterflow heat exchanger. If you consider this parallel flow to counterflow heat exchanger without changing the mass flow rate of the fluids as well as the inlet temperature of the fluid, then if you calculate the LMTD for parallel and counterflow, the LMTD for counterflow will be always greater. Since LMTD is greater, your total heat transfer rate associated with the counterflow heat exchanger will be higher compared to that of parallel flow heat exchanger, provided mass flow rate and inlet temperature of the fluids are maintained constant. So in practical cases, we always prefer a counterflow heat exchanger to a parallel flow. Next is overall heat transfer coefficient of a heat exchanger. We have already discussed the overall heat transfer coefficient in the first module. Consider a tube-in-tube heat exchanger or a concentric tube heat exchanger. Concentric tube heat exchanger is an heat exchanger formed by two concentric tubes. One fluid will be flowing through the inner tube and the other fluid will be flowing through the annular space between the inner and outer fluids. Here we can see that hot fluid is flowing through the inner tube and cold fluid is flowing through the annular space. So heat from the hot fluid is convected to the wall of the inner tube, then it is conducted through the inner tube wall and is convected to the cold fluid in the annular space. This is how this heat transfer is taking place. So we can see that this heat transfer consists of combined conduction and convection process. So we have to consider overall heat transfer coefficient. So if you consider overall heat transfer coefficient, we can express overall heat transfer coefficient in two different methods or ways. Overall heat transfer coefficient based on the inner surface area, the expression will go like this. And for overall heat transfer coefficient based on outer surface area of this inner tube will go like this, where R0 and Ri are the radii of inner outer and inner surfaces. Similarly, Hi and Ho are the heat transfer coefficient on the inner and outer surface of the inner tube. If the thickness of the inner tube is small, then we can approximate R0 equal to Ri. Under such condition, the second term in both the expressions of Ui and U0 vanishes. Moreover, Ri by R0, this ratio becomes 1. Then we can see that Ui and U0 will have same expression, that is 1 by U equal to 1 by Hi plus 1 by Ho. So from this expression, you will be able to find out overall heat transfer coefficient. Once the overall heat transfer coefficient is known, you can put it in this equation along with the LMTD, then you can find out what is the total heat transfer rate associated with this heat exchanger. It is all about this session. We'll meet you with numericals in the next session. Till then, bye.